Example 9.8, page 265. We have two blocks, M1 and M2 are moving on a frictionless track. Mu equals to O. Initially, M1 is moving with 4 amp per second to the right, and M2 has V initial equals to minus 2.5 amp per second to the left. I want to calculate the velocities of M1 and M2 after the collisions. Let me explain before the situation. Here we have state 1. Let's say state A. State A just before collision, and we have state B during the collision, where we have a compression of the spring, and finally we have the final state where I have no idea about M1 and M2, the velocity. We can say we have V1 prime and V2 prime. You know, we have a light spring. Light spring is attached to M2, and during the collision, we have a compression between M1 and M2. Okay, first of all, let me explain the situation and ask you, do you have or have you a elastic or non-elastic collision? You know, if we have non-elastic collision, you must have a conversion to the internal energy. Okay. In this case, we don't have a conversion to the internal energy. We don't have one object passes through another object. We don't have one object collides to another object and continue to move with a final velocity together. So as we don't have this internal energy, we can say directly we have elastic collision. We can write, we can say no conversion to internal energy, so we have elastic collision. Let me write before, in the case of elastic collision, first of all, P initial or P at any position equals to P final. This is equation 1. The second equation, the kinetic energy in the case of just before collision equals to the kinetic energy in the case of just after collision. And you know, in the case of elastic collision, you can write directly the relation between V1 and V2. We have V1 V1 initial minus V2 initial equals to minus V1 final minus V2 final. You can use this relation directly without calculation. And you know, also we have the relation V1 final in terms of the initial value, and also we have V2 final equals to M1 minus M2 divided by M1 plus M2 V1 initial plus 2M2 M1 plus M2 V2 initial, or V2 final equals to 2 M1 plus M2 M2 minus M1 plus M2 V2 initial. Okay, you can use any one of these equations. You know, if I take this one, I have V1 initial, I have V2 initial, I can calculate V1 final. Also, this one, I can calculate V2 final. So let's take the first method. First method. Here, I take this one and this one. You know, V1 final equals to M1 minus M2. I want to write the numerical values. So by using these two equations, we substitute the value of M1 and M2 as you see here in this equation. And you get the final value of V1 final equals to minus 3.3. So V1 final or V prime 1 is the same, okay? V1 final equals to minus 3.3 m per second. It means the object is moving in the negative direction to the left. And here, this object with the spring is moving to the right, plus 3.12. Okay, here we have also V2 final. Okay, let me use another method. We can use this one. I can take, for example, this one and this one. Pi initial equals to P final. Excuse me, P initial equals to P final. Initially, we have V1 and V2. So we can say P initial equals to P final. So we can write M1 V1 initial plus M2 V2 initial equals to M1. Okay, I take this state after the collision. M1 V1 final, M2 V2 final. Okay, M1 equals to, equals to 1.6. V1 initial equals to 4. M2 2.1. V2 equals to minus V2 initial minus 2.5. In function of V final 1 and V final 2. We can get the first relation between V final 1 and 2. So we get the first equation, this one, the relation between V1 final and V2 final. Okay, let's take this relation. V1 initial, okay, V1 initial minus V2 initial equals to minus V1 initial equals to 4 minus V2 initial equals to minus 2.5 equals to minus V1 final plus V2 final. This is the second relation between V1 final and V2 final. You can use your calculator to calculate V1 final and V2 final. You use this one and this one. You can find V1 final equals to minus 3.3 m per second, and V2 final equals to I think plus 3.12. Let me see. Right, okay, we get the same answer. So I show these two methods to calculate the final velocity of M1 and M2. Let me second part B. During the collision, so I am talking about this point. During the collision, at the instant block 1 is moving to the right with a velocity 3 m per second. This is during the collision. We don't have the maximum here. In this case, we don't have maximum compression, okay? When V1 has 3 m per second, I need to calculate V2. Okay, it's clear. Now I am talking about the case of during the collision. Okay. Here, in this case, during collision, when V1 has this value, I have to calculate V2. Okay. Now, how can we solve this problem? You know, in general, P initial equals to P final for any configuration. Before, during, after, before, after the collision, you can use this relation. I think it's the better solution to find this situation. We can take state 1 just before collision, and we can take state 2, or we can take state A and state B. State A just before collision, state B during collision. Okay, before collision, we have velocities. We have M1 V1 plus M2 V2 equals, we can put V1 final, or we can say V1 as you like, okay? But here I take initial and final in the state A and final in the state B. Okay, in the state A, we have M1 equals to 1.6, V1 equals to 4, M2 equals to 2.1, V2, we can say here initial, okay? Initially, minus 2.5 in this state A. State B, we have M1 V prime V1 final plus M2 V2 final, okay? M1 equals to 1.6. I take V1 final equals to 3 in this case during the collision. So M2 equals to 2.1 times, I need to calculate V2 final with this configuration. But you know, during the collision, when V1 final is going to the right, and V2 final is going to the left, because we can have during the collision, look, this block is moved to the right. We have a compression is moving to the right. We have the maximum compression. After, this block will move to the left. And here also we are during the collision. Okay, we arrive to a point, we have a separation, and we get the final state when we have the final separation of the two blocks. So here I take during the collision when M1 is moving to the right and M2 is moving to the left. Okay, so I need to calculate V2 final. We must have a negative value, because in this case, V2 final is going to the left. So we get V2 final equals to this value. We can say V2 final vector equals to minus I 1.74 m per second. In the case where V1 final equals to 3I m per second. Okay. Part C. Okay, let me write part C. Part C, I want to determine the distance the spring is compressed at that instant. Okay, when we have V1 final equals to 3 m per second and V2 final equals to minus 1.7 m per second, I have to calculate X. Okay, so here we have during the collision with this situation, here V2 final equals to minus 1.7 I m per second. Okay, I need to calculate X. Okay, here as you like. As we need to calculate X, so I have to talk about the mechanical energy, because in the case of P initial and P final, we don't have X. So I need to calculate or to talk about the mechanical energy between which point and which positions. We can take between position A and position B. Okay, as mu equals to O between these two positions. So we can say we have a conservation of mechanical energy. We have mechanical energy initial equals to mechanical energy final between state A and state B. Okay, so kinetic initial plus potential initial equals to kinetic final potential final. As you see here, we have the same level. We don't have H. So we have only elastic potential energy. We can talk about PE elastic. PE elastic. Okay. Initially, before the collision here, we have velocity. So we have kinetic. We can say m1 over 2 times 4 square for the first one. For the second one, we have m2 over 2 times minus 2.5 square about the kinetic energy. About the elastic, initially we don't have X because the spring is at X equals to O. We don't have compression, so equals to O. As the final state, we have velocity and we have elastic compression. So we have m1 over 2 times V at this position equals to 3 square plus M2 over 2. V here equals to minus 1.7 square. And about the elastic collision, we have K over 2 times X square. As you see, we have M1, we have M2, we have K equals 600. So we can calculate X equals to, so X equal 0.173 meter. Now let's take part D. Part D, what is the maximum compression of the spring during the collision? So, you know, M1 is moving to the right and M2 to the left. We arrive to a point where we have, and we get a maximum compression between M1 and M2. Okay, so here, if you will continue, let's draw on the same figure. Here, if we continue the compression of the spring, we arrive to the final position where we have a maximum compression between the blocks. Okay. Okay. Here we have M1 and here we have M2. Listen, the velocity of M1 is not equal to the velocity of M2. The mass of M1 is not equal to the mass of M2. So when we have a maximum compression, we don't have zero velocity. Be careful. Let me explain this point. If we have a big truck is moving on the road. Okay, we have a big truck. Let's say a big truck, and here is moving to the right, and here we have a small, let's say, object is moving to the left. When we have a collision between them, and let's say here we have a small spring. When we get a collision, the system will not stop. Okay, will not stop. Continue to move. Maybe as we have a big object here, the system will continue to move to the right. But as the maximum compression between the big one and the small one, we can get this maximum compression. The system will not stop, but continue to move to the right because the big one has more charge, more force to push the small one to the right, and the system will continue to move to the right. So we can say here at the maximum position, here the system has the same velocity, but it will be to the right because we have a big object here. So we can say here when X is max at this point, at this point, the M1 and M2 have same speed only at this point. After, okay, you will get a separation between them, but at the point where X is maximum, we have the system will move with the same velocity. After this point, you will get the separation again. Okay, I need to calculate X maximum. Here, as you like, you can use a mechanical energy between this point A and the point of maximum compression. You can. But the problem here, we don't have the velocity anyway. And you can use P initial equals to P final. P initial state is a state A just before collision, and state final is when we have X maximum. Okay, so we can use this relation. Maybe you can solve this problem with two methods. Let's write this relation between this one and this one. You can say here state C, because state B, we had another configuration. We have velocity here and velocity here. State C, where X is maximum. Okay. What about P initial? Initial here, we have M1 times 4, M2 times minus 2.5 equals, at this point, we have M1 and M2 have the same velocity, V is moving to the right. We can say V, you can say V final, as you like. As you see here, we have all the values. Why I am using this relation? I need X maximum, but I need V to calculate X maximum. So by using this relation, we can calculate V at this point, and after that, we can use the mechanical energy to find X. Here, we have M1 equals to 1.6. Okay, we can do the calculation. We get finally V equals to 0.311 m per second. It's a positive value. So when we have X maximum, the system will move to the right at this point with V equals to 0.311 m per second I. Now I want to calculate X. We can take also between A and B as mu equals to O. We can say E mechanical energy initial equals to mechanical energy final. Initially, we have kinetic equals to 1.6 divided by 2 times 4 square. Kinetic of V2 equals to minus 2.5 square. And you know, in this situation, we don't have X plus O equals, and at this point, we have velocity and we have compression. So we can write here the system is M1 plus M2 divided by 2. All have V square plus K over 2 X maximum square. Excellent. Now we can calculate easily the value of X maximum. We do the calculation. We get X maximum equals to 0.253. Let me resume. In general, for elastic and non-elastic, you have to know if we have elastic collision or non-elastic collision. If we have a conversion to internal energy, we have inelastic. If we don't have, we have elastic. Okay? We have elastic. Anyway, in the two cases, P initial equals to P final at any configuration, for any configuration. About the mechanical energy, you can ask yourself, do you have friction? So delta mechanical equals to omega F. We don't have friction, we can say delta mechanical equals to O. And we have a conservation of mechanical energy. Okay,